Hello, class. Okay, so we talked about the Biot-Savart law, which is something that can be used to calculate magnetic fields. And comparing to what we did in electrostatics, the Biot-Savart law is kind of like Coulomb's law. And after Coulomb's law, we talked about Gauss's law, which is kind of a different approach to it. But in some cases, Gauss's law can be used to calculate electric fields of certain charge distributions. And we're going to do something similar for currents and magnetic fields and talk about something called Amperes law. And I'm just going to write down Amperes law. Well, let's draw a picture first. Let's say we have a current coming out of the board. And remember the second right-hand rule, field lines curve around like this. So, and current, of course, should be in the middle. And I'll write down Amperes law. And then kind of explain it. So, in the Biot-Savart law, we have mu naught over 4 pi. Here in Amperes law, if we only had Biot-Savart law, why not just, we made up this constant, why not just call it mu naught? Well, the reason is Amperes law. Amperes law is actually considered more fundamental than the Biot-Savart law. So this constant that we use is defined in terms of Amperes law, and so we had to modify a little bit for the Biot-Savart law. But, so this is a mathematical expression of your Amperes law. So first thing to notice, it's an integral, it's a line integral, because we're integrating, over ds, where ds is a line segment. And this little circle around the integral, that means we have to consider a closed curve. So again, looking at Gauss's law, we had a closed surface. So you can have open or closed surfaces, like just this sheet of paper is a surface. That's an open surface. There's two sides to it, and a closed surface, just like a ball or something. That would be a closed surface. So here, a closed curve could be something. It could be a circle. Could be something like this. This would be an acceptable curve to use Amperes law because it is closed. Okay, so the left side, what we do is we take the integral of b dot ds. So let's say we have, this is our Amperian curve, and let's say at some point the magnetic field looks like this. So again, we're integrating, so we have to consider line segments. And let's trace, we have to pick a direction. Let's trace this line segment counterclockwise. So we're going around this counterclockwise. And that gives a direction out of the board. So just keep that in mind. For a counterclockwise from the right-hand rule, out of the board is our positive direction. And so since we're going counterclockwise, ds is in this direction. And so in this case, b dot ds would be negative, or at least along this segment. And so again, it can be positive or negative. And in magnitude, that would just be b ds cosine theta, where theta is the angle between these two vectors. And so we can find b dot ds for that segment, and then integrate along the entire curve. And what Amperes law is saying is that this integral is proportional to the current. Now, to be clear, what current are we talking about here? And because we have a closed curve, that it encloses an area. And so the current is whatever current is passing through this area. So, let's say we have a current going into the board. Let's call that I1. That's going into the board. And that would be consistent with a magnetic field going in that direction from the right-hand rule. So notice that, out of the board is our positive direction from the way that we're tracing the our curve. The current is negative, but notice that B dot ds also gives us a negative, so it's consistent. And so, Now, we'll come back to this in a minute, but let's look at a simple case. Let's say we have a current coming out of the board, and let's say the curve is just a circle like this. We're going to show that Amperes law is consistent with the Biot-Savart law. So let's say this is our current coming out of the board. We have I coming out of the board. We're going to trace this circle. It's a closed closed path. So we can do that. And let's do the integral B dot ds. Now, B dot ds, the magnetic field lines circle around. They form circles centered on the wire. And our curve is circular. And so I'll just do this down here, or here. In this case, B dot ds is just B ds. Because, if you look at any segment here, obviously the ds and the B vectors are going to be parallel. And so, B dot ds is just B ds. So we can simplify this a little bit. And there's one more thing we can do that's very nice. We know that every point on our curve, we're integrating over ds, this line that we drew around the wire. And every point is the same distance from the wire. And so the magnetic field has to be constant in magnitude along our curve, because every point on our curve is the same distance. And so we can do this. We can say that's equal to B times the integral of ds. And remember, ds is just a line segment. And so if we, by integrating ds around this thing, we have a circle, we're just breaking it up into pieces. So we have like ds1, ds2, ds3. Those are all the length of those segments. So when we go all the way around, we've completed a circumference. And so this is equal, I'll just write this result here. That's equal to B times the circumference, which is 2 pi r. And according to Amperes law, this is equal to mu naught I. So let's divide, let's solve for B. So we get the same thing we got before. We have just a current, a straight wire, and we know that the magnetic field should be mu naught I over 2 pi r. So Amperes law is consistent with Biot-Savart law. And this was a very easy calculation to do. However, what's interesting, what if we move this wire over here? Does that change anything? And the answer is both yes and no. In one sense, it changes a lot. If you're going to evaluate the integral b dot ds, well, good luck with that. That's going to be extremely difficult. Because the direction, like the dot product, is going to be, not parallel anymore. We can imagine the magnetic field lines around this wire will have different values and directions at different points along that curve. We'll keep our curve the same. I should use black for this because I use red for magnetic fields. So let me just redraw this. This is our curve. And so if we put our wire here, the magnetic field lines are going to look like this. It's a horrible circle, that last one, but you get the idea. You can see like the, if you look at this segment here, B is going to point this way, ds is pointing that way. You're not going to get this nice result here, and B is certainly not something you can take out of the integral, because a magnetic field to this wire is going to be much stronger here than over here. So this you'd actually have to do, you'd basically have to stop here. You could do this. Actually, you have to stop here. You'd have to have b ds cosine theta, where theta would be a factor all the way around this curve that we're integrating. So I asked, does anything change when you move the wire away from the center? And I said the answer is both yes and no. The answer is yes, because doing this integral, if you wanted to evaluate that, that would be a very different problem. However, the result would be the exact same. If you did do that integral, you would find that it's equal to mu naught I. And so it's kind of like Gauss's law in that sense. So it's Amperes law is a very profound result. It's not something obvious at all. And so again, you can imagine changing the shape of your wire, still same thing. But let's go back. So we're tracing our, let's talk about this I for a moment. Because right now, so far, we've considered just like a wire crossing, like crossing the region defined. We have a closed circle, so that has an inside and an outside. And so here, we have this crossing through. So let's call that I1, and let's call this I2, and let's say this is I3. So how would we write down Amperes law for this? Well, we have the integral of b dot ds. Now again, we decided to do this integral, or to define our curve to be going counterclockwise. So out of the board is our positive direction. And so this is equal to mu naught. And I'm going to write it I2 minus I1. Because out of the board is our positive direction. I2 is coming out of the board. I1 is going into the board. Now what about I3? I3 is not crossing this area enclosed by the surface, so it doesn't matter. If we had an Amperian loop that looks like this, and we put I3 out here, the integral around this loop would be 0. Now again, if you actually integrated it, that would be a complicated integral. If you approximated it as a sum, for instance, if you look at like a finite number of pieces, and you calculate b dot ds along each of those pieces, very likely none of those would be 0, but when you add them up, you're guaranteed to get 0. Some will be positive, some will be negative. And so you will get 0 for the sum if you were ever to do such a thing, but you'd have to be kind of sadistic to do something like that, or maybe that's not the right word. But you have to enjoy pain to try to integrate something like this. Yeah, that's Amperes law. And again, we used it to calculate the magnetic field in one case, where we had this long straight wire. Now, that doesn't always work, just like Gauss's law. And again, if you compare this to the Biot-Savart law, this was trivial. But it involved two things. First, this dot product had to be able to be something very simple that we could just, get rid of the vector, basically, nature of it. And also we had to take B out, and then we just had this integral ds, which is the circumference, regardless of the shape. It's the perimeter anyways. And that allowed us to, B times something, and then we could solve for B. That's not the normal situation, though, where this happens. It's only when you have certain symmetry involved. And there's two examples besides a long straight wire that we're going to consider. One of them is a solenoid, and the other is something called a torrid. I think I'm actually going to do these in separate videos, though. So, I'm going to stop this one here. We covered Amperes law. So, that's what it is. Now, just like Gauss's law, Amperes law is considered fundamental in electromagnetism. More so than the Biot-Savart law. Just like Gauss's law is considered more fundamental than Coulomb's law. And ultimately, we're kind of building up the subject of electromagnetism. We talked about electricity, now we're talking about magnetism. And just like mechanics is based on Newton's laws of motion, those are the fundamental laws that govern the entire subject. We're kind of building up something similar for electromagnetism. The fundamental laws of electromagnetism, there are 4 of them, and we've already covered 2, maybe even 2.5. One of those is Gauss's law, another is Amperes law. And I said 2.5 because very soon we're going to talk about something else about magnetic fields, which is actually called Gauss's law for magnetism. And so in a sense, we're almost 3/4 of the way done to getting to the foundation of this subject. One little thing I should point out, Ampere came up with this law. He was one of the greatest scientists of his time. This was a very big deal, along with his other contributions to physics. But this law actually has a flaw in it. But more on that later. So I think I'll stop this one here. And then I'll have separate videos on the applications of Ampere's law.